Hello everyone. Today, more curses at videos, cause but also, just in some general videos, you know, but mostly curse at. Real quick though, since this just appeared, I want to show you guys something. There we go. What? Why? All right, hold on. Give me a sec. Real quick. I have to change the YouTube accounts for some reason. Hey Pixin, how you doing? This is terrible, never mind. There we go. Well, I guess we won't be watching that then, which is unfortunate. Kind of sad, really. How do you like the greatest high skin? Hold on. Because I really want to see this. I don't understand. Why? My account shouldn't be age restricted, like what the fuck? Hold on. Yeah, I don't know why I have age restrictions. That doesn't make a whole lot of sense, but whatever. Shit, where do I even look at that? Advanced settings, maybe? No. 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 Privacy ads. Shit, I don't even know where I'd look at that. Well, that's dumb. And wait, hold on. No, I've restricted mode off or whatever, so I should be able to see it. Huh. Well, that's dumb. I want to watch it. I want to watch the God of War trailer, but okay. I guess we won't be doing that then. Wait, hold on. There we go. Mid.
Watch this. I can show you how to get the biggest discounts online when you shop at major retailers like Amazon.
But what do you mean it was good?
All around the world, marijuana is being decriminalized or even made legal. But is this really a good idea? In the online
I don't really want to look at weed. I don't really care. Real with you. I don't smoke weed. I don't care. Let's go with wormholes. Let's start out strong.
If you saw a wormhole in reality, it would appear round, spherical, a bit like a black hole. Light from the other side passes through and gives you a window to a faraway place. Once crossed, the other side comes for the interview, with your old home now receding into that shimmering spherical window. But are wormholes real, or are they just magic disguised as physics and maths? If they are real, how do they work, and where can we find them?
I would love to know what a wormhole is, though. I would love to. Right there.
For most of human history, we thought space was pretty simple. A big, flat stage where the events of the universe unfold.
Let me see.
Even if you take down the set of planets and stars, there's still something left.
That's true.
That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect two very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper.
Why?
General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds.
So what I'm getting is basically like, according to math, it's real. That's weird. Like, you can calculate something that's not real, but theoretically possible. It's weird.
The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards.
Huh. So, alright, so I think what he's gonna say. So it's either it's a parallel universe, right? Or it's or you know, if you go into a black hole, you go into the future. I think what he's about to say next.
In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang.
Well, isn't there a
This is called a white hole.
Yeah, then we have it.
Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky, and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings called...
So it's like a piece of paper. Okay, so it's like a piece of paper. You can just go through. Okay.
cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out though, but that's okay. There might be an equally extremely hard way to get our hands on a wormhole. We could try to make one.
Yeah, you know, I ain't gonna lie to you. That sounds like a movie plot, and the whole point of the movie is to not make a wormhole. You know, it's try to prevent a wormhole from being made by some super evil company, because that sounds like I don't think we should mess with wormholes. But I think I understand what he's saying here. So basically, you know, we have you know, our universe, our existence right here, right? And then the wormholes, like you go here and then if you go in, you go all the way over here, right? And it's basically you're just, you know, traversing Like you're going across time, like you're going across space. So I'd fast forward too much.
Wormhole, we could try to make one. To be traversable and useful, there are a few properties we want a wormhole to have. First, it must obviously connect two distant parts of space-time, like your bedroom and the bathroom, or Earth and Jupiter. Second, it should not contain any event horizons which would block two-way travel. Third, it should be sufficiently sized so that the gravitational forces don't kill human travelers. The biggest problem we have to solve is keeping our wormholes open. No matter how we make wormholes, gravity tries to close them. Gravity wants to pinch it closed and cut the bridge, leaving only black holes at the ends.
Fucking ads. I'll away with you.
Whether it's a traversable wormhole with both ends in ours, or a wormhole to another universe, it will try to close unless we have something propping it open. For very old string theory wormholes, that's the cosmic strings job. For man-made wormholes, we need a new ingredient: exotic matter. This isn't anything like we find on Earth, or even antimatter. It's something totally new and different and exciting, with crazy properties like nothing that's ever been seen before.
Does it exist?
Exotic matter is stuff that has negative mass. Positive mass, like people and planets and everything else in the universe, is attractive because of gravity. But negative mass would be repulsive. It would push you away. This makes a kind of anti-gravity that props open our wormholes. And exotic matter must exert enormous pressure to push space-time open, greater even than the pressure at the centers of neutron stars. With exotic matter, we could weave space-time however we see fit.
So
We may even have a candidate for this exotic matter, the vacuum of space itself. Quantum fluctuations in empty space are constantly creating pairs of particles and antiparticles, only for them to be annihilated an instant later. The vacuum of space is boiling with them, and we can already manipulate them to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our wormholes.
So you're telling me you can make something out of nothing? Because, you know,
Space is boiling.
telling me the vacuum of space, we can make something out of nothing.
With them,
I don't know how the fuck
and
we
we
do
can
that.
already
I hope it
manipulate
explains
them
it,
to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our
Well, I suppose you
wormholes.
Right.
Once we're keeping it open, the ends would start together, so we'd have to move them around to interesting places. We could start by wiring the solar system, leaving one end of each wormhole in orbit around the Earth. We could fling others into deep space. The Earth could be a wormhole hub for a vast interstellar human civilization spread over light years, but only a wormhole away.
So like Guardians of
However,
the Galaxy.
wormholes have a dark side. Even opening a single wormhole kind of breaks the universe in fundamental ways, potentially creating time travel paradoxes and violating the causal structure of the universe.
I see.
Many scientists think that this not only means they should be impossible to make, but that it's impossible for them to exist at all. So for now, we only know that wormholes exist in our hearts and on paper in the form of equations.
Well,
We know you
hold on. So, okay, but the rest of this is just an ad. It's just a promotion. But if it's proven on paper, right? I know it's the whole thing of, you shouldn't take an idea off of paper, like, just because it looks good on paper doesn't mean it's actually good in practice. But, if you mathematically calculated it, I think that means that it would work, like it could work. What about solar storms?
I'm Dr.
Since
Jeff
16
Finneker,
was
and today we're going to
gone.
explore the science of the sun and other stars.
He said, "Hey, private."
the sun, smooth
To
and
be fair,
round
he's probably trying to get a Halloween skin.
and peaceful. except when it suddenly vomits radiation and plasma in random directions. These solar flares and coronal mass ejections, or CMEs, can hit Earth and have serious consequences for humanity. How exactly do they work? How bad could they be? And can we prepare for them? While the Sun seems pretty solid, it's actually like a very hot ocean. So hot that it rips atoms into electrons and nuclei, all flowing around each other in a plasma. This plasma is pushed around and shaped by the Sun's magnetic field, similar to how the Sun's gravitational field reaches out to the planets and shapes their orbits. But magnetism is very different from gravity. Magnetism is one part of a dual force, electromagnetism. Electricity creates magnetic fields, and magnetic fields create electricity. On the Sun, the plasma made of electrically charged protons and electrons creates a magnetic field as they move, and this magnetic field then shapes the flow of particles. They're stuck in a dynamic feedback loop called a dynamo, which keeps the Sun's magnetic field alive. This magnetic field stores enormous amounts of energy and leaks out over the solar system. It carries with it a constant trickle of solar plasma like a light rain known as the solar wind, creating a sort of space weather. But it isn't always calm and smooth. As the Sun's plasma churns and flows around itself, its magnetic field gets all kinked and twisted. This creates magnetic knots that build up enormous amounts of energy. When the magnetic knots break, like a tangle of springs exploding outwards, the Sun can vomit plasma and other awful things into the solar system. These solar storms come in many types, like solar flares, a tidal wave of high-energy radiation. They race through the solar system at the speed of light, sweeping up protons in the solar wind, accelerating them into a high-speed solar proton storm. Then there are coronal mass ejections, which rip millions or billions of tons of plasma from the Sun's atmosphere, catapulting it through the solar system at speeds of up to 9 million kilometers per hour. When these monsters hit us, nothing happens on Earth. While even smaller storms can damage satellites, affect radio communication, or be dangerous to astronauts, for people on the surface, space weather is harmless. Earth's atmosphere protects us from the worst effects of a solar flare by absorbing the blast of X-rays high up in the atmosphere, well before it reaches the surface. The electrified plasma from a CME is deflected by the Earth's magnetic field, diverting the energy storm to the north and south poles, where energetic particles fall into the atmosphere, causing the atmosphere to glow and creating beautiful auroras.
Oh, that's cool.
As with any sort of weather, most of the time things are fine. Sometimes there are hurricanes though, or in the case of the Sun, solar superstorms. And we know that they happen once or twice every century. If one were to happen today, we would first detect strong solar flares, a sort of flash before the much more dangerous thunder. The thunder is a CME, consisting of billions of tons of hot magnetic plasma that crosses the 150 million kilometers between the Sun and Earth in less than a day. When it arrives, it causes a shock wave that violently compresses the Earth's magnetic field and transfers energy into the magnetosphere. But it can get worse. If the magnetic field of the CME is aligned to Earth's in just the right way, the two magnetic fields merge. As the magnetic cloud passes over Earth, it stretches the Earth's field into a long tail. Eventually, the energy stored in the tail becomes too much to contain. It snaps and explosively releases its energy towards Earth. A geomagnetic storm has begun.
That sounds fun.
A few hundred years ago, nobody would have cared. This storm gushing over the Earth is not relevant for machines made out of meat and bones. But it's very relevant for machines made out of metal and wire. Remember the dynamo? Magnetism creates electric currents. Earth in the 21st century is covered in millions of kilometers of wires transporting electricity and a complex grid of machines like transformers that make this transfer possible. A CME's energy can induce currents in our power grid that can either completely shut it down or, worse, destroy the transformer stations that keep our grid running. This has happened already, like when the Quebec power grid failed after a strong solar storm in 1989. But in general, our engineers know how to deal with these storms, and so we usually don't even notice. The last time a solar hurricane washed over Earth was in 1859. The Carrington event, the largest geomagnetic storms ever observed on Earth. Massive auroras occurred as far south as the Caribbean.
Damn.
In some places, they were so bright that people got up thinking the sun was rising. Luckily, we only had one sort of modern technology, telegraph systems. They failed all over the world, shocking their operators and chucking out sparks. Today, we have a tad more technology, and our luck may run out soon. Another bad solar storm is bound to happen eventually. A storm as strong as the Carrington event missed Earth only by a small margin in 2012. Studies projected that it would have inflicted serious damage to electronic systems globally, costing up to $2.6 trillion to the US alone. The time to replace all the damaged systems was estimated at between 4 and 10 years. It's hard to say.
Christ. Damn, okay.
How bad it could have been. Experts disagreed. Some assumed there would just be temporary blackouts, but others worried it could be much worse. We won't know for sure until a big solar hurricane hits us. The probability of such an event is estimated to be 12% per decade. That's about a 50-50 chance of at least one in the next 50 years. And there is more unsettling news. A 2019 paper found that even calm stars like our Sun can create superflares every few thousand years. Eruptions orders of magnitude stronger than the strongest storms we have observed in the solar system. If such a storm hits us unprepared, the consequences could be catastrophic. It's hard to overstate how much we depend on electricity. It's not just the lights at home, it means no computers, no communication, no navigation. A sustained power outage might lead to a breakdown of the supply chain, water supply systems failing, and hospital generators running dry. Supermarkets not being refilled while food rots in the fields. The lack of power might make it extremely hard to reboot our broken power grid, taking years or decades to restart our starving civilization. Okay, time to panic. As much as daily newspapers might like for solar storms to send us back to the Stone Age, they probably won't. Fortunately, even though solar storms aren't preventable, virtually all of their nasty side effects are. Scientists observing the sun have a few hours up to a few days to see a CME coming. And the engineers working the systems that keep the world running are well aware of the risks posed by solar storms. Transformers and substations can be taken offline. Short preventative blackouts, or in other words, by unplugging stuff. Engineers can open up extra lines to dissipate the extra power. And with investment and upgrades cheap compared to those other natural disasters require, we could protect the world's electric grid against even the nastiest of storms. But we do need to prepare. While the risk is manageable, it is real. For while our sun bathes us in warm and pleasant light, one day it might send a monster our way that we better be ready for. This video was sponsored.
You know, I mean that's pretty interesting that at any point in time, you know, because I don't think most of us have like our electric grids to that level where it can take that, because cost effect, cost and all that. And I haven't heard any news about, our electricity is not protected against whatever, against solar flares. But what's interesting though, is like, if that were to happen, I mean, 10 years without electricity, what would happen to like a country, right? Like America, I'm gonna be real with you, I'm pretty sure it would just devolve into not a country. It would be at most a state thing, be based on state. But I think what's interesting is this. Imagine seeing an aurora borealis in like I don't know, like in the Caribbean. I mean, shit must be, it's beautiful, yeah, but like, damn. Kind of wish I was there. Well, what do you think the people thought in like, like 15, I mean, during that time period, like, why do we have this thing in the sky? Ooh, I like this one.
If you shop on Amazon, you should use this tool. It's a browser extension that...
Imagine NASA announced today that they found aliens. Bacteria on Mars, weird alien fish in the oceans of Europa, and also ancient alien ruins on Titan. Wouldn't that be great? Well, no, it would be horrible news. Devastating even. It could mean that the end of humanity is almost certain and that it might be coming soon. Why? Why would the most exciting discovery of our lifetime be bad? Let us imagine the development of life from its inception to us today as a flight of stairs. The first step is dead chemistry that needs to assemble itself into self-replicating patterns, stable and resilient, but also able to change and evolve. The second step is for our early life to become more complex, able to build more complicated structures, and use the available energy much more efficiently. On the next step, these cells combine to become multicellular beings, enabling unbelievable variety and further complexity. The step above sees the species evolve big brains, enabling the use of tools, culture, and shared knowledge, which creates even higher complexity. The species can now become the dominant life form on its planet and change it according to its needs. First, shy attempts to leave its planet are happening. This is where we are now. It's in the nature of life as we know it to reach out, to cover every niche it can. And since planets have a limited carrying capacity and lifespan, if a species wants to survive, it will look for more places to spread to. So the steps above the current ones seem logical. Colonize your own solar system, then spread further to reach other stars. To the possible final step, becoming a galaxy-wide civilization. It's very likely that this is a universal principle for civilizations, no matter where they're from. If a species is competitive and driven enough to take control over its planet, they'll probably not stop there. We know that there are up to 500 billion planets in the Milky Way, at least 10 billion Earth-like planets. Many have been around billions of years longer than Earth. But we're observing 0 galactic civilizations. We should be able to see something, but there's nothing. Space seems to be empty and dead. This means something is preventing living things from climbing the staircase beyond the step we're on right now. Something that makes becoming a galactic civilization extremely hard, maybe impossible. This is the Great Filter, a challenge or danger so hard to overcome that it eliminates almost every species that encounters it. There are 2 scenarios. One means we are incredibly special and lucky. The other one means we are doomed and practically already dead. It depends on where the filter is on our staircase. Behind or ahead of us. Scenario 1. The filter is behind us. We are the first. If the filter is behind us, that means that one of the steps we passed is almost impossible to take. Which step could it be? Is life itself extremely rare? It's very hard to make predictions about how likely it is for life to emerge from dead things. There is no consensus. Some scientists think it develops everywhere where the conditions are right. Others think that Earth might be the only living place in the universe.
I doubt that.
Another candidate is the step of complex animal cells. A very specific thing happened on this step, and as far as we know, it happened exactly once. A primitive hunter cell swallowed another cell, but instead of devouring it, the 2 cells formed a union. The bigger cell provided shelter, took care of interacting with the environment and providing resources, while the smaller one used its new home and free stuff to focus on providing a lot of extra energy for its host. With the abundant energy, the host cell could grow more than before and build new and expensive things to improve itself, while the guest became the powerhouse of the cell.
The powerhouse.
These
All right, so if this so-called gray filter is behind us, I think that's it right there. Because if scientists say it happened exactly once, you know, like we don't know the statistics of it happening over, how many every years, but if it happened only once,
cells make up every
and it
animal on
doesn't
the
find
planet.
us, I think that's probably
Maybe there are billions of bacteria-covered planets in the Milky Way, but not a single one, apart from us, has achieved our level of complexity or intelligence. We humans feel very smart and sophisticated with our crossword puzzles and romantic novels, but a big brain is, first and foremost, a very expensive evolutionary investment. They are fragile. They don't help in a fistfight with a bear. They cost enormous amounts of energy. And despite them, it took modern humans 200,000 years to get from sharp sticks to civilization. Being smart does not mean you get to win automatically. Maybe intelligence is just not so great, and we're lucky that it worked out for us. Scenario 2. The filter is ahead of us. Plenty of others died already. A great filter before us is orders of magnitude more dangerous than anything we encountered so far. Even if a major disaster killed most of us or threw us back thousands of years, we would survive and recover. And if we can recover, even if it takes 1,000,000 years, then it's not a great filter, but just a roadblock to an eventual galactic civilization. On universal timescales, even millions of years are just the blink of an eye. If a great filter really lies before us, it has to be so dangerous, so purely devastating and powerful that it has destroyed most, if not all, advanced civilizations in our galaxy over billions of years. A really daunting and depressing hypothesis is that once a species takes control over its planet, it's already on the path to self-destruction. Technology is a good way to achieve that. It needs to be something that's so obvious that virtually everybody discovers it, and so dangerous that its discovery leads almost universally to an existential disaster.
war.
A large-scale nuclear war.
Yep.
Nanotechnology that gets out of control.
Yep.
Genetic engineering of the perfect superbug. An experiment that lights the whole atmosphere on fire. It might be a super-intelligent AI that accidentally or purposely destroys its
I doubt
creators.
that. Because
All
if that
things
were
that we
true, then
can't
that
even see
means
coming right now.
black hole.
When I say
But if
cereal,
that's
you
true,
say dinner. Cereal.
then
Okay,
look,
I'll
the
go
AI,
marinate.
then we would still see it.
I'm
It would be
Dr. Jeff
branching out to other
Finneker, and
planets, I
today
think,
we're going to explore the science of the sun and
to
other
get more resources to expand it.
Or it's way simpler. Species competitive enough to take over their planet necessarily destroy it while competing with each other for resources. Maybe there are runaway chain reactions in every ecosystem that once set in motion are not fixable. And so once a civilization is powerful enough to change the composition of its atmosphere, they make their planet uninhabitable 100% of the time. Let's hope that that's not the case. If the filter is ahead of us, our odds are really bad. What we can hope for. This is why finding life beyond Earth would be horrible. The more common life is in the universe, and the more advanced and complex it is, the more likely it becomes that a filter is in front of us. Bacteria would be bad, small animals would be worse, intelligent life would be alarming. Ruins of ancient alien civilizations would be horrible. The best case scenario for us right now is that Mars is sterile, that Europa's oceans are devoid of life, and the vast arms of the Milky Way harbor only empty oceans hugging dead continents. That there are billions of empty planets waiting to be discovered and to be filled up with life. Billions of new homes waiting for us to finally arrive.
That reminds me of something. Hold on. I want to see if this is true. Oh, wait, hold on. Could by 1 point just beneath this. Sorry about that. That bacteria could survive 1.2 million. I'm asking sometimes. So, that's not good. That's really not good. that is yeah, I thought I heard some news about some bacteria being found on Mars. I mean, it's not the worst, you know. It's not the worst thing, as he said. Like he said it would. Well, what did he say it would be? It would be alarming or something like that.
This is why finding life beyond Earth would be horrible. The more common life is in the universe, and the more advanced and complex it is, the more likely it becomes that a filter is in front of us. Bacteria would be bad.
Yeah. So bacteria would be bad. To be fair, though, maybe the light of these new civilizations just hasn't reached us, right? Because from what I've heard, I'm pretty sure it would be if you were in another galaxy, right? You would still, I think, not galaxy, but I think if you were in, somewhere outside our solar system, I think if you're like 2 solar systems away or something like that, you would still be seeing humans as monkeys, right? And you're just only like 2 solar systems away, you know? I mean, so maybe the reason why, ancient, alien civilizations haven't found us yet is because we're just too new of a civilization. However, based on this, I think it'd be terrible if we found civilizations, you know. So, I want there to be life out there, but now I'm just kind of like, it's like, but maybe they can help us, you know. Their option, there isn't a filter in all the galaxies of what doesn't hide because we're that place. Bruh.
What makes Morgan and Morgan different is that you're not just a case, you're an actual person.
But yeah, that's interesting though.
We're crunching tons of polygons here.
Yeah.
What's going
But
what if our universe comes with a self-destruct button to eliminate itself so cleanly and efficiently that every single physical thing would just stop existing and life would be impossible forever? The ultimate ecological catastrophe. Vacuum decay. To explain how our universe could destroy itself, we need to understand 2 principles. 1. Energy levels. A core idea in physics is that everything has an energy level. The higher the level, the more energy is in the system. Wood, for example, has a high level. It can be burned, a process that releases the chemical energy stored in its molecular bonds and turns it into heat. The ash left over is at a lower energy level than the wood before. 2. Stability. Everything in our universe tries to move towards its ground state, in which it's completely stable and has as little energy as possible. For example, a ball on a hill is unstable and has a lot of potential energy. When disturbed, it will roll down into the valley and lose its potential energy in the process. The ball is now in its ground state and stable. It will remain like that. Everything in our universe follows these 2 principles. If something has a lot of energy, it's unstable and wants to get rid of it to become stable and reach its ground state. This is true for every system, even in the weird world of quantum mechanics. If our current understanding of physics is correct, then the universe gets its properties from quantum fields. We explained them in detail in another video. For this video, imagine them as the rules of the universe. They tell particles how to behave and interact. Like everything in the universe, they want to be in the lowest energy level possible, which is called a vacuum state. This has nothing to do with vacuum in space. It's just called this way because scientists are bad at naming things. We think all the fields reached their vacuum state, except maybe one. It's possible that the Higgs field is not stable, but metastable, which is a fancy way of saying that it pretends to be stable, but really is not. It would be a false vacuum. The Higgs field is responsible for giving particles their mass, which rules how almost everything in the universe interacts. What would happen if the Higgs field is in a false vacuum? Think of our ball in the valley. The ball is the Higgs field. The valley might not be the lowest energy state for the Higgs field. There might be an even deeper valley that it wants to get to. This would mean that the Higgs field has a lot of potential energy waiting to be released. The Higgs field could be like a piece of wood, but drenched in gasoline, waiting to set the universe on fire. A random spark, like quantum tunneling, could release the potential energy of the Higgs field. This could happen at any time and without warning. If at any point in space this so-called vacuum decay starts, there is no turning back. As the Higgs field crashes into the lower energy state, it releases a massive amount of potential energy. This energy pushes the space around it over the barrier, which releases more potential energy. A sphere of the new stable Higgs field, or true vacuum, grows at the speed of light in all directions. Imagine it like setting a sea of gasoline the size of the universe on fire. The sphere is surrounded by a shell of energy that devours everything it comes into contact with. Whatever it touches is eliminated from existence. The bubble will continue to grow forever, deleting the universe on its way. There is no way to be warned since it's so fast, but there's nothing we could do anyway. Our destruction would be instant. In a fraction of a second, Earth would be gone. But it actually gets worse. If the energy level of the Higgs field changes, it changes all of physics. In the true vacuum of the sphere, the standard model will be overthrown, superseded by different physics that we don't know. How fundamental particles behave, how atoms hold together, how chemicals react. Vacuum decay won't just destroy life, it will destroy chemistry itself, making life as we know it impossible. We simply have no idea what it would be like inside. It might be a shadow of what it is now. Or not. We don't know. If vacuum decay happens, the outlook is indeed grim. If you feel slightly worried now, don't be. At this point, false vacuum is speculation based on our current understanding of particle physics, which might be wrong.
Okay.
It's kind of like using a ruler to measure a continent. Sure, you can do it, but you might be off by quite a bit at the end. Right now, no one can say if vacuum decay is a thing that's real or just a scary idea. But even if one or multiple spheres of death have already started expanding, the universe is so big that they might not reach us for billions of years. If they're far enough away, they might not ever be able to reach us because of the expansion of the universe. The speed of light is not that fast on the scale of the universe. So while vacuum decay
Because
is
the only thing
fascinating,
that's faster than light, I think, right? It's as fast. It's either as fast as light or it's faster.
scary, right now there are other things we should be more afraid of. In contrast to vacuum decay, we have the power to prepare for most of them.
Oh, okay. I see. So maybe that's the Great Barrier, is just vacuum decay, and that would be scary. That's interesting. So what if the great filter is in front of us and that's it? Well, going off of that, it could also be behind us because maybe we're in a position where it never reaches us. Don't know. Oh yeah, he mentioned this video. I want to watch it.
Tex-Mex and margaritas.
What is something?
Oh, margaritas and Tex-Mex.
See y'all at Chewy's.
Find your purpose at Grand Canyon University. Visit gcu.edu.
The simple questions are the hardest ones to answer. What is a thing? Why do things happen? And why do they happen the way they do? Let's try to approach this step by step. What are you made of? You are matter, which is made of molecules, which are made of atoms, and those are made of elementary particles. But if elementary particles are the smallest things that exist, what are they made of? To answer a simple question, let's start simply. Let's wipe the universe clean, away with matter, antimatter, radiation, particles, anything. Now let's take a closer look at absolutely nothing. What is empty space? Is it what we call a vacuum? There are no atoms, no matter, nothing. Is it really all that empty? Nothing gives us the building blocks for everything. In a sense, empty space is a lot like a vast, calm ocean. While the water is very still when nothing is happening, a stiff breeze can create some serious waves. Our universe works a lot like this. There are these oceans everywhere. Physicists call them fields. This might be strange and new, but think about radiation, for example. By exciting what's known as the electromagnetic field, a little kink is created, which is the particle we call the photon, the particle that carries radiation. We perceive it as light. This isn't unique to light. Every particle in the universe is made this way. There are fields for every particle of matter, all with their own rules. For example, along with the electromagnetic field, there is an electron field everywhere in the universe, and little kinks in that field are electrons. Altogether, the fields of our universe can produce 17 particles, which can be divided into 3 categories: the leptons, and the quarks, and the bosons. Leptons consist of the electron as well as its cousins muon and tau particles. Each has an associated neutrino. Then there are quarks. The quarks are the nuclear family of particles. They're always found bound together in groups and pairs and make up protons and neutrons, which make up the nuclei of atoms. Together, the leptons and quarks are the matter particles. They make up all the things you see: the air you breathe, the sun that warms you, the computer you're using right now to distract yourself from the stuff you should be doing. But things don't just exist, they also do stuff. In some philosophical sense, the properties of a thing are just as much a part of it as existence itself. This is where the bosons and the fields that make them come into play. While the quarks and leptons are made by matter fields, the bosons are made by force fields. We call a rule of the universe a force, and so far 4 fundamental forces have been discovered: electromagnetism, gravity, and the strong and weak nuclear forces. These forces are the rulebook of a game where the pieces are particles and the game is the universe. They tell particles what they can do and how they can do it. Bishops move diagonally, massless particles move at the speed of light, knights can jump, gravity attracts. The forces are the rules for how particles interact, which ultimately make them the rules for how particles assemble into all the big things we see in the universe. Gravity isn't just the rule for orbits around the sun or apples falling from trees. As a rule, it says matter attracts, which builds planets and stars. Electromagnetism isn't just a rule for magnets attracting or repelling, or electric currents in light bulbs. It governs all atomic bonds, building every molecule. Together, forces and particles are sort of like the tinker toys of existence. The bosons are like messengers, passed between, you could say, connecting the matter particles, which they use to tell each other how to move. Each particle uses a certain set of the forces to interact with other particles. Quarks, for example, can interact with each other with electromagnetism and the strong nuclear force, but electrons don't use the strong force, just electromagnetism. The quarks exchange strong force bosons, communicating the strong nuclear attraction to each other, while the protons they build exchange particles of electromagnetism, photons, with the electrons. Thus, the quarks end up locked up in nuclei, while the electrons remain attached by their electric attraction, building atoms. Even though the universe has lots of big messy phenomena like life, supernova and computers that seem complex on the surface, if you zoom in far enough on anything, you just get 17 particles emerging from underlying fields playing a game with 4 rules. To summarize, in the most basic form we know right now, this is what things are. This theory is what physicists call the standard model of particle physics. You are basically nothing more than disturbances on an ocean that's excited by energy and guided by forces that make up the rules of the universe. But why? And what is a force? We'll have to explore a few more simple questions to get to the bottom of this. We made some wallpapers from some of the graphics in this video. You can get them on patreon.com. If you want to help us make more videos, you can do so there. We really appreciate your support.
I appreciate
While you decide, here are some more videos.
For making me feel smart. Alright, so I'm gonna cut it there. Because no one's here, and there's really, because the point of this is to talk to people, to talk to people about stuff. But if no one's here, then it is. Sometimes some days are just not that entertaining. It is what it is. I do need to get my average viewer count up though, as Twitch says. But I hope you guys at home have a great day. I'll have a great day, all that jazz. Tomorrow YBA, and I don't know. I think it'll be trying to get 12. I think. Yeah. No, I'll be getting it. That's right. Alright, other than that, see you guys tomorrow. Peace.